Good morning. Again, if you haven't turned in your vector worksheet that is due at this time, make sure you get that turned in back into the reading teacher's basket. We're cracking down on homework because we have to go. We got to pick up the pace this quarter because we've got to get. It's just how the calendar works out. It's one of those years where the ice, snow, cold, we had 3 of those days, those virtual days, fell on the wrong times. And they fell where we pushed things back farther than we needed to. And we've got to get to point A in order for you guys to do well in the NTC final. So we got to pick up the pace a little bit. So with us picking the pace up, we're putting more emphasis on homeworks now. And so homeworks in the fourth quarter might not necessarily always be to the day of the test. Okay? And probably, excuse me, more than likely, we haven't discussed this yet, but more than likely, homeworks are going to be due for everybody for the fourth quarter. So it's not going to be the 83% club like it was first semester. So, okay? So today we're going to go into the second half of section 6.1, and it actually falls in the old textbook. It falls in a different chapter. It's kind of goofy. We never really liked how that was set up. So we combined 6.1 navigation angles and navigation and that with vectors because that's really what it is. And some of you just got back from probably taking a plane trip last week somewhere, and as a pilot, the computer's doing most of it, but you're doing vectors constantly, okay? Because you've got wind vectors dealing with your plane vector, and you want to make it to, if I'm taking off from Wausau, let's say, from central Wisconsin, and I'm flying to Florida, and saying I'm going to use US Florida, okay? If I'm flying, and I just fly, I point the plane at where I want to go, and I just let it go, okay? Wind is going to take me, and it might push me way over here, and then it might push me way over here, and then it might push me way over here. Next thing you know, I'm in Bermuda, not in Florida, and people on the plane are not happy. Okay? And so that's how those kind of things, that's how this ties in with vectors, because yes, I'm pointing my vector there, but I might actually have to aim my vector over here in order to make it to there. Okay? So we're going to be naming angles many different ways today. And it's kind of confusing, but in the end, I think you'll see that it all works out as long as you know what's what. Okay? So, big change in this way. And these notes should be in your note packet too, if I'm not mistaken. After multiple forces, keep going past multiple forces. There we go. What's this one? It's on 4.8 bearing angles, note sheet. It's the page right before. It's the page right before the picture of Florida. Okay. So in trig, we had all of our angles were 0 degrees straight out to the right. We've ingrained that in your brains since we started the unit circle back in October, right? 0 degrees is over here on the right side. Positive angles go counterclockwise. They go up and around that way. Okay? So since October, we've ingrained that in your brain. Today, we're changing that. Okay? Now, navigation angles, 0 degrees is up north. Straight up is 0 degrees. And your positive angles are drawn clockwise. So that means that east is now 90 degrees. Straight out to the right now, instead of being 0, if we were in trig, straight out to the right is now 90 degrees. South is down. And that's 180 degrees. West is to the left, and that is now 270 degrees. One side note, your reference angles, we will be doing reference angles. Still are off the horizontal. We haven't changed that. So if you need to find a reference angle, it still would come off of the horizontal. Just now, well, we'll get into it here. As I say, 210 degrees is not 210 degrees anymore. 210 degrees is now, what's that, 240 degrees. So it's kind of a goofy type thing. So let's do some examples here of that. Okay. So our first example is these are navigation angles. Okay. So my navigation angle of 53 degrees. Okay. So I'd start with my crosshairs. 0 degrees is up top. 90 degrees is over here. So 53 degrees would be right here. So that gives me a navigation angle of 53. Agree? Here's the problem. Here's the rib. If we're going to use that in a problem, we need to know its trig angle, because we're going to use the trig angle anytime we're doing calculations in the problem. So what is a navigation angle of 53 degrees is trig angle. 37 degrees, yeah. Put that in a different color. Hold on. We'll change the post. What would this angle's reference angle be? It would also be 37 degrees because it's in quadrant 1. Okay. With me? Alright, let's try a little harder one now. So my navigation angle is 195 degrees. Which quadrant is a navigation angle of 195 degrees in? Quadrant 3, right? Okay, because we start up here, here's my 0, here's my 90, here's my 180. So a 195 would be down here. Trig angle. What would my trig angle be for this same 195 degree navigation angle? I start here and I go all the way around. Answer, what do you got? 255. Yep. Reference angle. What would my reference angle be? 75. Yep. That would be right here. Questions on that? All right. You try those two. So I want you to, one, draw the navigation angle. Find me the trig angle. Find me the reference angle for those two. $70 will put my 300 degree angle up there. So that's my nav angle. That's going to give me a 30 degree reference angle. That's going to give me 150 degree trig. So my trig angle will be 150 degrees. My reference angle would be 30 degrees. Everybody agree with me on that? 127, I'd have 0. I'd have 90. I'd have 180. 127 would be down here. Give me a reference angle here of 37 degrees. That would give me a trig angle here of 323 degrees. Agree? Good times. Let's put this to work now with Florida. A speedboat, I know it's a picture of a sailboat. I get it. I understand. Okay? All right? Oh, you guys, oh, look at you guys have a speedboat. We changed it on yours, we didn't change it on ours. I don't know why. Hold on, tap the brakes. Let's see what this, if there's a link going on with this one. So, the reason, here I'll bring it, I'll just pull it right over onto it. I don't know why I'm loading two of them. So, a knot, okay, is a unit of speed equal to 1 nautical mile per hour. Now, a nautical mile is different than a regular mile. Okay? So, a nautical mile is, I gotta think now, what is it? It's like it's 1/60th of 1/360th of, I don't know, that's just, what's an nautical mile? So it's based off of the circumference of the Earth. A nautical mile, if you were to cut the Earth in half at the equator, so that's the circumference, okay? You divide that into 360 degrees, then you would divide that, I get it. Then you would divide that into 60 minutes, and 1 minute of arc, so 1/60th of 1/360th of the circumference of the Earth is called a nautical mile. Okay? Which ends up being, I think I go into it in this article. It ends up being 1.1508 miles, or 6,070 feet. You'll never have to know that. We're just telling you what it is because there's knots in this problem. Okay? So that's what it's, a knot is a nautical mile per hour. Sailors used it because it used to be that was the only form of transportation in the world. Okay? So a speedboat travels at a speed of 40 knots from Fort Lauderdale. Okay, so that's where my sailboat is. You've got a speedboat. On a course of 65 degrees. Okay? So for me, what I would do then is I would put a little crosshairs at Fort Lauderdale. And from that, then, we've got to go 65 degrees. Well, that 65 degrees is going to go out here in that general direction, right? Where this angle right here is my 65 degrees. It's going to travel along that path. Now, we're saying that the Atlantic Ocean currents mean nothing. Okay? They took a break for the day. Okay? It's going to travel along that path for 2 hours. So how long is that length? Knots is the speed. So it'd be 80 nautical miles. Yep. So this would be 80 nautical miles. Then it changes course. So now I'm going to put another crosshair there, and it changes a course to 155 degrees. Okay, well, 155 degrees would be down this way, where this angle right here is 155 degrees. It travels on that course for 4 hours. So how long is that segment? How long is that segment? 160 nautical miles, because it's traveling at 40 knots still. Now, when you're doing these problems, the words matter. This word right here, you may not think as very important, but that word right there, that from, is hugely important. Because the distance is going to be the same. But if I'm standing at Fort Lauderdale and I'm the Coast Guard because now they've got a problem, my bearing, my navigation to that boat is different than if I'm the captain of the boat and I want to go back to Fort Lauderdale. Those are not the same navigation angles. With me? Because you're in two different spots. Okay? So the word from says determine the distance and bearing from Fort Lauderdale, which means we need to find that distance and we need to find that angle. Okay? Well, we know some things. We know the fact that the crosshairs are all parallel, right? The horizontals and the verticals are all parallel on our crosshairs. So if this is 65 degrees, then this angle here would also be 65 degrees. We know that if this angle here is 155 degrees, then this angle here is how much? This little teeny tiny angle in here. 25? Because it's got to go to 180. So all told, this angle right here in that triangle is how much? 90. Our life just got a heck of a lot simpler because now we've got a right triangle, so SOHCAHTOA is in play. If SOHCAHTOA weren't in play, then we'd have to rely on law of sines, law of cosines. Okay? Okay? So now that we know it's a right triangle, what do we have at our disposal? We have tangent. We also have SOHCAHTOA. We also have, we got the Pythagorean theorem. So we can find x by just doing the Pythagorean theorem. Agree with me on my calculations. Okay. So the boat is 178.89 nautical miles from Fort Lauderdale. Okay. We can find this angle right there. How can we find that angle? Tangent. Okay. So that angle, let's call it theta, is going to be the inverse tangent of what? 160 over 80. So that's the inverse tangent of 2. And I get the inverse tangent of 2 is 63.434948882 degrees. Agree? Side note, if you haven't figured out, you're going to need a calculator every day, pretty much every day for the rest of the semester. Because we're going to be doing straight up calculations the whole time. Okay? So that's that one. Now, my question to you is, what is that bearing? Because that angle that we just found is just that triangle angle.
That would be that angle
Plus 65? Because to get back to due north, I've got this blue 65 in there also. So my bearing would be, what's that, 128.43? Yes? Love it. Now, we're going to set up this problem, and this problem is going to be due tomorrow at the beginning of class for you. It's your homework for this evening. Okay? So a shoreline runs north and south, and a boat is due west of the shoreline. That's key, because now what do we have? We got a right angle, right? Okay. The bearings of the boat from, key there, the bearings of the boat from 2 points 300 feet apart on the shore are 240 degrees. So 240 degrees would be not quite far enough. Where this angle here is 240 degrees. And so now the second point, the 260 degree point, is it going to be above that point or below that point? Below? Why below? Yep, exactly. Yep. The angle's bigger, so that means that it's got to be below. Now, we also know that this distance here is 300 feet. Okay? Based off of that, what are we trying to find? Boat to the shore. So is that green, red, or black? The black. We're trying to find this distance there. Okay? That's your task for tonight. Okay? Find me that distance.